Welcome to the chapter on x86 assembly languages. So as we shall see, x86 is just not one assembly language, it's a family of assembly languages. They are used by the Intel and AMD processors, which at least as of 2016 dominate the laptop, the desktop and the server processor markets. So these slides are for chapter 5 in the book Computer Organization and Architecture, published by McGraw-Hill in 2015. The book should be available in almost all geographies around the world. You can always let the author or the publisher know if a book is not available in a certain geography. So let's come to this very interesting family of ISAs. So the first point is that it's actually not one ISA. It is a family of ISAs, but all of them end with 86. So that's the reason it's x86, where x can mean a lot of things. So the great grandfather in the family is the 8-bit 8080 microprocessor used in the mid 70s. And say the 8080 microprocessor used to have an assembly language of its own. It was an 8-bit processor. The grandfather is the 16-bit 8086 microprocessor, which was released in 1978. And for those days, it was a fairly revolutionary microprocessor because 16-bit was also rare in those days. And the microprocessor pretty much started the era of microprocessors, and gradually large server computers started being built of much smaller microprocessors. So the parents in this generation are the 32-bit processors, namely 80386, 80486, Pentium 1 till Pentium 4. So all of these the processors used to dominate in the 90s and early 2000. So pretty much for 20 years these processors dominated. Finally, Intel and AMD, so they moved to 64-bit processors. Again, 32 bits or 64 bits basically means that the smallest unit of storage inside the processor is either 32 bits or 64 bits. Alternatively, this means that the size of a register is 32 bits in a 32-bit processor and is 64 bits in a 64-bit processor. And even the size of memory addresses that can be issued by the processor and so on. In one case is 32 bits, in other cases 64 bits. So examples of 64-bit Intel processors would be Intel Core i3, i5 and i7. So the latest Intel processors that we use. And similarly, examples of AMD machines would be AMD Opteron and AMD Bulldozer, which are the latest AMD processors that are used. So the main features, so again, why is the name of this architecture x86? Because as you can see from the previous slide, there are a lot of microprocessors with the suffix 86, 8086, 80386, 486, Pentiums, Intel Core i3, i5, i7. So all of them pretty much use the same kind of assembly language. And the nice thing is that assembly language for i5 is also uh, a superset of the assembly language of the earlier microprocessors. So which is great. And since 86 is at the end of every assembly language or processor line, at least till 486, the name of the ISA per se is x86. So x86 is a CISC ISA, unlike ARM and Simple RISC. So it has 300 plus instructions. And so that is the basic ISA, at least the one that we are concerned with. But if you consider all extensions and so on, then as of 2016, the number of instructions are roughly 1,000. So instructions can have a source or a destination memory operand. So it's a CISC instruction set. So the operands themselves can be far more complicated. And so the number of registers are actually few. And another major difference as compared to Simple RISC is that it uses the stack for passing arguments and return addresses, unlike registers. So in other RISC ISAs, we had a lot of registers. So we were using the registers for passing arguments and return addresses. and similar kinds of information, but this does not happen over here, and it uses a different memory model called segmented memory. So we shall look at all of these points in detail over the next few slides. But an important point that I want to make at this stage is that the x86 ISA is per se an advanced ISA. See, if you are reading this chapter or listening to this video without a basic understanding of assembly languages, you will find it somewhat difficult. Because as I've been stressing all through, walking and chewing gum at the same time, or trying to understand a certain assembly language, as well as the fundamentals of assembly languages, both are not possible at the same time. So it is possible to do only one but not the other. So what my suggestion would be is that readers can go to chapter 3, get a broad idea of what assembly languages are. They need not read chapter 4, which is about ARM assembly languages, so that's not required. But at least my assumption at this stage would be that for all the readers or listeners who want to move forward, they have a basic idea of what assembly languages are. So this will really help them. Otherwise, they'll find this chapter fairly difficult to understand because their fundamentals would pretty much not be there yet. Alright, so the way that the chapter will proceed is that first we'll discuss the machine model. Then we discuss simple integer and branch instructions. x86 has fantastic memory instructions, advanced memory instructions. So we'll discuss that. We'll discuss floating point instructions because floating point instructions are fairly complicated in the x86 ISA. And lastly, as we did for ARM and Simple RISC, we'll discuss methods to encode the x86 ISA. So let's take a look at the view of registers. Modern Intel machines are ISA compatible with even the oldest 8086 processor. So what this essentially means that any kind of program which was meant for the 8086 processor can still run on a modern processor. So this is mainly done due to market requirements. So if a market requirements suggest that a 64-bit processor has to be ISA compatible. What means by ISA compatible is that programs written for earlier processors, older processors, which had 32-bit and 16-bit ISAs, should still be able to run with a 64-bit processor. And the market requirement is as follows. Let's assume that a certain company has a lot of programs written for 32-bit processors, and because they need some additional performance, they buy a newer processor from Intel. And this newer processor has a 64-bit ISA. It would be a very bad idea for the company to discard all of its code and essentially rewrite or recompile the code for the newer processor. There are several reasons for this. First is that the original developers might be there, not there. The source code might not be available. It might be a lot of work. There are issues with robustness and reliability of the code. So because of so many issues, most companies, most customers of Intel and AMD would want that whatever code they had, that should still run with the advanced processors. Advanced processors can add more features, but they should not break something which was already running. So keeping this requirement in mind, both Intel as well as AMD ensure that their latest process can still run code which was written, can still run, let's say, a binary which was written 30 years ago. So the question is, what do we do with our set of registers? Do we have a separate set of 16-bit registers, a separate set of 32, and a separate set of 64-bit registers? Is this a good idea? It's probably not a good idea because we don't have that much of space inside the processor, and because of performance constraints, it's not what we should be doing. So we should definitely not define a new set of registers for each kind of ISA, and that's a bad idea, so we have to look for a better idea. So let us consider the 16-bit x86 ISA. The 16-bit ISA had 8 registers. They were called AX, BX, CX and DX, SP, BP, SI and DI. So actually the idea of these registers had actually come from the 8-bit processor whose registers were of the form A, B, C and D. But in any case, when they made a 16-bit processor, they named the registers, so which was way back in 1978, AX, BX, CX, DX, SP, BP, SI and DI. So SP is the stack pointer. So recall from chapter 3 that the idea of the stack pointer was introduced. Stack pointer. BP is actually the base pointer, so we'll discuss what it is. So essentially when we enter a function, we save the initial value of the stack pointer in the base pointer. So we will discuss this when we come to how functions are implemented in x86. Then we have the registers SI and DI. So SI actually stands for source and D for destination. So this will be clearer when we discuss instructions that use the SI and DI registers with, in a special form. So for the time being, it is sufficient to just simply remember that S stands for source and D for destination. So in the 16-bit processor, we had only these 8 registers. And so if you would recall, both ARM and Simple RISC had more registers, they had 16. But x86 in that sense is fairly conservative in terms of the number of registers. In 8, we have 4, general purpose registers AX, BX, CX and DX. SP has a special meaning, it's a stack pointer. BP also has a special meaning, it's called the frame pointer or base pointer, depending upon how it's implemented. And SI and DI can be used for regular computation, but they have a special meaning. S stands for source and D for destination. So some instructions assume that SI is a default source and some other instructions assume that DI is a default destination. So we shall look at these instructions later in this lecture. So the question is, should we keep the old registers and create a new set of registers in a 32-bit processor? We already realized that that is a bad idea. That's not what we should be doing. The main thing being that the area in which the registers are there, it's fairly cramped. So if you consider that area of the processor, you have registers, you'll have functional units like adders and multipliers, and you'll have many other kinds of structures, right? So you can consider it as, think of it as like a downtown of the processor. So this particular area is very, very cramped. And so it's not a good idea to sort of increase the set of registers. So this is definitely a bad idea. So what we can do is that we can widen the set of 16-bit registers to 32 bits. So we shall see in the next few slides how this is done. So if the processor is running a 16-bit program, then it can sort of think that every register is 16 bits wide. And how will it think? It will use the lower 16 bits of every 32-bit register to essentially save its value. So let's take a look at this particular figure. So this figure is very important. We'll keep on referring to this figure. So it's very important that readers get a very, very good idea of this figure before proceeding. So let's first consider the first 8 registers which are there in the 64, 32 and 16-bit variants. So in these registers, let's assume that the processor is running a 16-bit program. So the registers that it sees are AX, BX, CX, DX, SP, BP, SI and DI. So AX is actually the lower 16 bits of the EAX register. So consider E as extended AX. So the EAX register is a 32-bit register which is seen by a program when it is running in 32-bit mode. So essentially we can divide a 32-bit field into 2-bit fields 16 bits wide each. So the AX part is the lower 16 bits of the EAX register. Similarly, DX is the lower 16 bits of the EDX register, and likewise. So we just extend this idea to 64 bits as well. So instead of EAX, we define RAX, which is 64 bits wide. The upper 32 bits are essentially part of the 64-bit mode, but the lower 32 bits store EAX. And out of this, again, the lower 16 bits store AX. So if you consider this, so this is the same picture for all the 64-bit registers: RAX, RBX, RCX, RDX, RSP, RBP, RSI, and RDI. So what is exactly happening till this point? What is happening is that a 64-bit processor will have these 8 registers, which are 64 bits wide, from RAX till RDI. So it'll have some more, so we'll discuss them, but let's focus on the top 8 first. So the top 8 registers will be 64 bits wide, and it'll have only these top 8 for with these names. Now if we have an instruction that accesses EAX, EAX in this case would basically mean the lower 32 bits of RAX. So what the processor will do is that it will read the RAX register, discard the upper 32 bits, and take the lower 32 bits and return the value. The same is true for a write. So let's assume that in a 64-bit processor, we try to access SI. So if we try to access SI, what the processor would do is it will first, and let's say we're trying to read SI. So it will first try to read the RSI register. So out of the 64 bits, it will only consider the bottom 16 bits. This is what SI corresponds to. Similarly, if we want to write to SI, then what the processor will do is it will write to the lower 16 bits, least significant 16 bits of the RSI register. So essentially, it all depends on how we view this set of registers. If we view the set of registers as 16-bit quantities, then we access the lower 16 bits of every register. And so let's consider one more example. Let's assume that we have a 32-bit processor. In a 32-bit processor, clearly the registers RAX, RBX will not be there. So what this basically means is that if I write a program with, let's say, RAX in a 32-bit processor, this will clearly be an error. But if I write EAX, it is fine. So it is essentially the first register. And I can always write AX. So AX will be the lower 16 bits of the first register. So what we are doing, in a nutshell, to summarize, is that every register is being viewed in multiple ways. The storage area is the same, but it's just that our view is changing. So when we say that, let's say the name of a register is SP, what we mean is the lower 16 bits of pretty much the first, second, third, fourth, fifth register. So the lower 16 bits of the fifth register. Similarly, when we say ESP, it's the lower 32 bits of the fifth register. And when we say RSP, it is essentially the fifth register whose length is 64 bits. So it is possible for any processor that implements the x86 instruction set to define these set of registers, and it all depends on how many bits is the processor, how wide is the processor. If it's a 64-bit processor, it needs to define RSP, ESP, and SP. If it's a 32-bit processor, clearly every register is 32 bits. So it is meaningless to define something like RAX or RBX or RSP because 64 bits cannot be supported. But at least we can say that the full 32 bits will, let's say, be referred with the E suffix. And for the 16-bit register, we consider the lower 16 bits. So the advantage here is that we are not wasting any space. The code is pretty much compatible. So the code of, let's say, 16-bit Intel processor can easily run on a 64-bit Intel processor because the set of registers are all there and we have not created any extra space for them. All we are saying is given let's assume that an assembly code for a 16-bit processor had CX. what we will do is that we'll generate code which will tell the processor to access RCX and then consider the lowest 16 bits. So in this case, it is just a question, this is actually a very neat way of designing the set of registers. It keeps the clients happy, it keeps the customers happy. Well, it does not keep the designers very happy because it makes their life slightly difficult, but actually not that difficult as we shall see in chapters 6, 7, and 8. And but the most important thing is that the compatibility of code is there. So tomorrow, if Intel releases a new processor, then we'll be sure that all the code that we have, right, all the binaries that we have, will actually run. In addition, the 64-bit ISA defines 8 extra registers, R8 to R15. And mind you, R8 to R15 do not have any of these subfields because the 16 and 32-bit ISAs, the 16-bit and 32-bit Intel ISAs only defined 8 registers. So for these 8 registers, they are appropriately mapped to different fields inside large 64-bit registers. But R8 to R15 are 8 extra registers which do not have any subfields, and they can be used by 64-bit Intel processors and Intel binaries. But mind you, any binary generated for a 64-bit processor will not run on a 32-bit processor, but neither should it be. Right? So you always want whatever programs you write to be compatible with future processors. You don't want any program that you write today to be compatible with processors of the past. Right? So this is sort of a general rule that most companies follow, and that's the reason this particular design decision has been made. So before I leave this slide, I would again like to underscore the importance of this particular slide. It's very, very important that readers and listeners understand this slide. And basically the important takeaway point is that the register is the same. Given a program, if the register will just be interpreted in different ways. So if we write AX, we'll only interpret the bottom 16 bits. If we write EAX, we'll only interpret the bottom 32 bits. And if we write RAX, we'll interpret essentially all 64 bits in a 64-bit processor. So x86 can actually takes the argument slightly further. So it can even support 8-bit registers. So the AX, BX, CX and DX fields are further subdivided into two 8-bit fields. So this is to ensure that we are compatible with some of the earliest 8-bit processors. So in this case also, it helps us write slightly more efficient code if we need to access values at a byte level. So because compatibility with 8080, which was a 8-bit processor, is not really that important, but this allows us to access information at a byte level, which is much more important today at least. So here the lower 8 bits or the lower 1 byte is represented by AL, BL, CL and DL, L for lower. Similarly, the upper 8 bits or byte is represented by AH, BH, CH and DH. So in this case, the idea is the same. It is exactly similar as this particular figure, where we take a register and divide it into several subfields and interpret the fields based on our instruction. So in this case, we further divide the top 4 16-bit registers into 2 subfields each, AHAL, BHBL, CHCL and DHDL. Alright. So along with the general purpose registers, which can be used for all assembly programs, And they can be used to do regular arithmetic computation and everything. So these are pretty much multi-purpose, general purpose registers. x86 defines two more registers. The first, but these registers cannot be used by the assembly programmer and cannot be manipulated by the assembly programmer. So it can be read, but it cannot be manipulated. So these registers are manipulated by the system. So first we have the R flags register. So similar to our terminology in the previous two slides, the R flags register is 64 bits. Its lower 32 bits can be interpreted as the E flags register, and the lower 16 bits can be interpreted as the flags register. So flags, E flags and R flags. Same way as AX, EAX and RAX. So the flags register is exactly similar to the simple RISC flags register or the ARM CPSR register. So what it does is that it contains the results of the latest comparison. So comparison, so there are many bits, many subfields in this flags register. So one of them is overflow, OF. So this is set if the previous operation can be in compare, and there are some other operations which can set the flags. So readers who are interested can take a look at the x86 manual and they'll find out all the flags that any instruction can set. So the overflow flag is set on an overflow, and so this can be read from the flags register. Similarly, we have a CF or a carry flag which is set on a carry or borrow. So let's assume I'm doing an addition or a subtraction. So the carry flag CF is set if the addition results in a carry or the subtraction results in a borrow. Then we have the zero flag ZF, which is set when the result of a comparison or result of any other instruction which can set a flag has led to an equality. So let's say we are comparing A and B, or let's say, in terms of assembly language, we are comparing registers EAX and EBX, right? So let's say the values, if EAX is, equal to, I'm writing equal to in C style. If EAX and EBX are the same value, the zero flag will be set. And then we have SF or the sign flag, which is the sign bit of the result. So the sign bit of the result will essentially indicate if the result is negative or non-negative. Non-negative means positive or zero. So these four bits can be set in the flags register. So there are other bits as well. Readers can take a look at Intel's manual for the other bits, but these are the four main bits. So the idea over here is that this flags register or E flags or R flags, depending upon the processor and the assembly language, stores the flags in exactly the same way as the simple RISC flags register used to, or the ARM CPSR register used to. So the idea here is that any instruction like a compare, which can set the flags, will essentially set the flags based on its result. And then the flags can be used by a later instruction, such as a branch, to base its decision on what exactly this register contains. So this also has 16, 32 and 64-bit variants. Similarly, the PC, the program counter, is known as IP or the instruction pointer in x86. This is exactly what the PC is. So this cannot be set by a user, but user means the programmer or the program. But the program can read its value, and so there are instructions actually to read its value. It can't be read or accessed directly. But using instructions, there are methods to read the value of the program counter. So the program counter is called the IP register in 16 bits, EIP register in 32 bits, and the RIP register, extended instruction pointer register for 64 bits. It's called RIP. So the idea is the same, that the same register is divided into multiple fields, And depending upon the nature of the instruction set and the processor, we choose which field should be returned as the answer. So now let's take a look at the floating point registers. So so we didn't discuss the floating point registers in x86 and ARM, mainly because ARM has added floating point support somewhat late, and so it was not a good idea to have it as a part of a basic course. But floating point support has been there in x86 for a long time now. So the floating point unit was sort of going back to history. In the 386 processor, right, 80386, the 386 processor, which was like released in the mid 80s, it did not have floating point support. So it was only possible to have integers. So an additional co-processor was used called the 387 chip to give it floating point support. But finally, when the 486 processor came, it had floating point support. So, those days, because not a lot of transistors were available in hardware, the architectures were somewhat more complicated. They were not very simple. And pretty much x86 has not been able to change that for the floating point, for the set of floating point registers. So they are fairly complicated. But I hope that after explaining how it works, after this slide, which is slide number 11, it will not look that complicated. So the complexity arises from the following fact. It arises from this fact that the set of registers can be addressed independently. So they can be addressed. So there are 8 floating point registers. So they can be addressed as ST0, ST1, or till ST7. So they can be addressed in that way. And the other is that they can also be addressed as registers that are part of a stack, a separate stack called a floating point register stack. So the way that we can think of this is that inside the processor, what we actually have is we have 8 locations arranged as a stack. A stack is any data structure which has a last in first out semantics, something exactly similar to a stack in programming languages. So consider a stack of books. So the book that we add at the end is on the top. Now if we need to remove any book, we start removing books from the top. So pretty much any book which was added the last will also be the first to be taken out. So it's the same for register values as well. So in this case, let's assume that we have a stack of 8 floating point values. So this is called the floating point stack or the FP stack. Now another interesting part is that these floating point registers, each floating point number actually has more precision than a double precision number. So instead of 64 bits, each of these registers is actually 80 bits, which is a huge mantissa. So it gives Intel processors a lot of precision. So we refer to the stack top as register ST0, and we refer to the bottom of the stack as register ST7. So there are instructions to push a value on the floating point stack. So once this is done, so let's assume that the numbers were initially of this form: 3, 4.5, 6. We just had 3 numbers. Now let's say we push 2 on the floating point stack. So the new state of the stack would be 3 would come here, 4.5 would come here, 6 would come down, and 2 will get pushed on the top. So now if we print the value of ST0, it will actually print 2, ST1 will print 3, ST2 will print 4.5, and ST3 will print 6. So this is where the complexity lies, that we can look at the set of floating point registers in 2 ways. We can either look at them as a set of registers or as a stack. It is better to look at them as a stack, where essentially the register gives you the position on the stack. So let me repeat. The floating point register actually gives you the position on the floating point stack. So a floating point stack is essentially a stack of 8 values. I'm just drawing it once again because this is a very important concept and students typically don't get it. So I'm trying my best to explain it in as many ways possible. So consider a floating point stack as a stack of 8 values, 8 floating point values. So let me draw 8 rectangles. Okay, let me draw one more at the top to make it 8. Alright, so we have 8 rectangles. So what ST0 basically means is that it's a register and its value is whatever is at the top of the floating point stack. Similarly, ST7 can also be treated as a register and its value is what is the last element in the floating point stack. So if I push or pop the stack, then essentially the elements move, so the value of these registers will also change. Right? So essentially it's not a register in a registered sense. It's only something which tells you that for this, so let's say for ST3, it tells you that for, let's say, the third position from the top of the stack or the fourth position in the stack, what is the value? So it is essentially, you can think of it as a numbered stack where it is possible to access the elements of the stack given its position from the top. So there are historical reasons why this has been done. So this is sort of reminiscent, if you still recall what was taught in chapter 1, that there are stack-based machines. So those days programming and writing code for stack-based machines was somewhat easy. So that's the reason this was done 20 or 30 years ago. But because of reasons of maintaining compatibility, it has become very, very essential to sort of keep the models, the programming models that used to be there, still. There's a need to keep them alive. Otherwise, your programs that were written for, let's say, the 486 processors will not work on i7 processors. And unnecessarily, companies that make x86 processors will lose business. So if let's say if let's say floating point registers were written as a stack, it's a good idea to maintain it. All right. So the view of memory is also not very easy. So ARM and Simple RISC viewed memory as an infinite array of bytes, right? So basically the memory first location was at location 0, next at location 1 and so on. So the x86 memory model is slightly different. So it is a von Neumann model, no doubt. So the instruction and data are saved in the same memory, but it is what is called a segmented memory model. So the idea is that each address in x86 is actually an offset from the start of a segment. So what we do is that if we consider this is memory, right? So any kind of a memory address, uh, so the way actually we think is that we sort of divide this into multiple segments, right? So this is one segment, this is one more segment. So it is an extension of a von Neumann model. So it's more like a Harvard model in that sense, a logical hardware model, but Harvard model, I'm sorry. But the idea is that given a large array, we are interested only in parts of the array called segments, right? So maybe, this part and this part. So the way that this works is like this. So let's consider the code segment which contains the instructions. So the starting address of the code segment is contained in the code segment register. So when we have the address of an instruction, so maybe let's say the starting of the code segment register points over here in memory. So when we have an address, what we do is that every address is specified as an offset from its corresponding segment register. So in this case, we take the value of the segment register, we take the value of the address and we add them, and then the result points to the memory address in which we'll find the data. So this can be extended as follows. This x86 supports 6 different segment registers. So each register is 16 bits wide. So we are essentially starting from the earliest days when segmentation was introduced. So we'll have a code segment. So what the code segment basically means is like this. So let's consider a conceptual view of memory where we treat it as a large, almost semi-infinite array of bytes. So I'm drawing a conceptual view of memory where each box is a byte. So the code segment register might, let's say, start over here. So every instruction in the program is specified as an offset from the code segment register. So maybe let's say there is an instruction whose address is 4. So we'll start from the code segment register and count 1, 2, 3, 4. So this instruction would begin from here. Similarly, we can have a data segment that contains all our data. So maybe this can start from here. So the data segment would be this wide. Let's call it the data segment DS. And similarly, this might be the code segment. We can then have a stack segment to store the stack of a function. So mind you, this is different from the floating point stack. The floating point FP stack is stored in hardware, but the stack is a programming language concept which was elaborately introduced in the second half of chapter 3. So your readers should definitely go back to those set of lectures or those videos and understand what a stack is all about. So the stack essentially stores the activation block of a function. What is an activation block? It stores all the arguments, the return address, all the temporary variables of the function. So this is called the stack. So the stack segment also has its segment register. And along with that, we have 3 extra segment registers, ES, FS, and GS, which are not used, but they can be defined if need be. So ARM, Simple RISC, and so on have a linear memory model where the address that is specified in the instruction is sent to the memory system, so segmentation is not required, right? So there are no segment registers. However, x86 does not have a linear memory model. It has a segmented memory model where, let's say, we divide our addresses into 3 types: code, which is regular program instructions; data, which is all the data that we would use; and then the stack. So data is pretty much global variables, and you can think of stack as local variables. So given our conceptual view of memory, we map these segments to different locations, and the segments and every single address is specified as an offset from its segment register. We will see this kind of a model has some advantages. We'll not be able to discuss a lot at this point of time. We'll actually discuss more of this in chapter 10, the chapter on memory system. But the idea basically is that this gives us some amount of security. Because what a computer virus typically does is that the computer virus tries to change the code of a program such that instead of doing its normal job, it does what the virus asks it to do. With a segmented memory model, this is somewhat difficult, but we'll appreciate all of this in chapter 10. But what can be understood at this point of time is that it will give us some advantages in terms of security. There are other advantages as well. For example, in early processors that were really memory constrained, it was possible to use this mechanism to actually work with a smaller amount of memory and keep on moving data between the hard disk and memory to support uh, larger programs. Those reasons are not very relevant today, but still there are issues of security that this model handles very well. So we'll look at them in chapter 10, where we'll show that for most viruses it is not possible to modify instructions in the text section of the program. That is because any stores are by default supposed to use the data segment and the instructions are in the code segment. So this gives us some amount of separation. So between the code and the data segment. So actually, I was not very accurate when I said this follows the von Neumann model, because physically, yes, physically it's the same memory, but logically It is more like a Harvard architecture where we are thinking of the code part of the memory and the data part of the memory is actually separate, right? So the code part and the data part, we're thinking of them as actually separate. So it is very difficult for instructions such as the store, which modifies data, to actually go and modify the code. And this actually makes it much harder to implement a malware such as a virus. So how does segmentation work? So in the 16-bit version, it had 6 segment registers. But nowadays with 64-bit, uh, with 64-bit systems, the segment registers will not be able to hold a 64-bit memory address. So what they actually do nowadays is that they contain an offset into a large segment descriptor table. And this is again because 16 bits are not sufficient to store a memory address. So again, just to show an example, so let's say the CS register, which contains the code segment, instead of pointing to a memory address, actually points to a location in a large system-wide table. You can call it a segment descriptor table. Uh, so in this case, so since it's a 16-bit quantity, this table can have at the most 2 raised to power 16 entries. So this entry will actually point to a memory address. And think of this, that this entry will actually be a memory address. So this is how modern processors work, that we still have 6 segment registers which can be modified by the operating system. What is an operating system? It's a special program whose job is to take care of the rest of the programs. So we'll again discuss what an operating system is in slightly more detail in chapter 10 and chapter 10, 11 and 12. Not 11 but chapter 10 and 12 mainly. But at the moment we can think of each segment register uh, still containing 16 bits. But in this case the 16 bits refer to an entry in a large table called the segment descriptor table. So Intel processors have two kinds of segment descriptor tables. There is something called an LDT segment descriptor table and a GDT, a global descriptor table. So the LDT is actually meant to be one per process. What is a process? A process is a running instance of a program. So this is typically not used nowadays. If it's not used, we'll not discuss it. The GDT is a global descriptor table. So the GDT is what we will discuss. And so pretty much this does not have 2 to the power 16 entries because we will typically not need that many segments. This is slightly smaller. It contains 8191 entries. So 8192 is actually a very special number. It is some time to guess. It is 1024 times 8, which is nothing but 2 raised to power 13. So we'll actually use 13 bits from the contents of the register to access this particular GDT table to read the starting memory address of the segment. And what are the 3 segments that we are interested in? The code segment, which contains all the instructions, the data segment, which contains all the global variables and the constants, and the stack segment, which contains all the local variables and function arguments and return addresses and so on. So these are primarily the 3 segments that we are interested in. And so the starting address of these 3 segments will be different for different programs in the system because they are shared. The memory, the large memory is being shared, and where these segments actually begin will definitely be different for all the programs in the system. But in any case, we don't care about this at the moment. All that we are concerned is that we will have a single large table, will be shared by all the running programs in the system, and pretty much every program can access this to find out where its segments begin. And each entry in these tables, in the GDT table in the per se, will contain the starting address of the segment. So now the question is, for every memory access, what do we need to do? For every memory access, let it be a store or a load. So we will pretty much generate an address, right? So we'll have a base register depending upon the addressing mode. We can use base offset or base index, or doesn't matter. Whatever is the addressing mode, we'll generate a memory address. In a 64-bit processor, the memory address will be a 64-bit number. In a 32-bit processor, the memory address will be a 32-bit number, so it doesn't matter. So with this memory address, what we need to do is we need to do something else. So let's say that we need to access the segment register, right? We need to find the entry in the GDT which for corresponding to the value stored in the segment register. We need to read that entry, add it to the memory address, compute the new memory address, and send it to, so compute the new memory address and send it to the memory system, right? So I'm just writing memsys over here. So this is this is pretty much the main idea, that if for any store or a load instruction which will have a memory address that the processor will compute, we need to add it with the contents of the relevant segment. So we need to add it with a number which is obtained as follows. We read the relevant segment register, we access the GDT. From the GDT, we get the starting address of the segment in memory. We add both to get the final memory address, and this is sent to the memory system. So does it mean that for every memory access we need to access the GDT or LDT? That would make things very slow. So let us instead have the same mechanism but try to speed it up. So let's use a segment descriptor cache, an SDC, at each processor that stores a copy of the relevant entries in the GDT, which is, in my opinion, our opinion, everybody's opinion, a much faster route. So what we do is that we define a shortcut. What we do over here is that we define a segment descriptor cache. We access that first, which is a very small and fast hardware structure. So this will keep the memory addresses of the segments that we are interested in. So we are typically interested in three segments: code, data, and stack. And given the fact that a processor at any point of time executes only one program, it can't do more. So we just need to access a small hardware structure which is processor specific, access the value and add it to the memory address. If we don't find it, or if the value is stale, then we'll have to go through this longer route. So I'll sort of cut this and say that this going via the segment descriptor cache is the default method. Just in case we don't find an entry, we need to take the much slower method, which is this method. So let me call this the slow method, right? So actually, ultimately they produce the same information. So I can put it over here and cut it right here. So this is the slower method and this is the faster method. So what is the idea? We look up the SDC first. If an entry is not there, then only we get it from the GDT and we populate SDC. Otherwise, we take the value from the SDC. So this method is very quick, fast and efficient, and almost hides the fact that we are adding an additional level of work to every memory access, right? So this fact all gets hidden with modern hardware, and we'll discuss how in chapter 9. But the important point to note that is that with a segment descriptor cache, things become really fast. You don't have to access the GDT for every single access, for every single memory access. Alright, so x86 addressing modes, given the fact that it's a CISC instruction set, are also somewhat complicated. So it is very important for us to get a general idea of what the addressing mode looks like before actually we move forward. So up till now, uh, listeners must have gotten a feel of the fact that x86 is definitely more complicated than most other instruction sets. And well, so no, that's where the C in the CISC comes from, right? Complex. But it's not that complex. There is some amount of, there's a large amount of elegance to it. So it's not that difficult. So let's take a look at this particular figure. So any memory address, this is the way that we actually specify it in assembly language. And this specification is translated into machine code as well. So we define a base register. That's the first thing that we do. So in the base register, we specify the segment. But mind you, this is optional, this field. So actually all of these fields individually are optional. So so this field is definitely optional. So let me write optional over here. So typically you will not find this being done unless it's a special case. So in any case, all of these fields are actually optional. So we will discuss that part later. So then we have a base register which can be any of the eight general purpose registers, and in 64-bit mode it can be the additional uh, registers as well. Right, there is no problem in that, but we will not discuss that for the time being. So let's proceed with the rest of the lecture. Assuming that we are talking about the 32-bit instruction set, right? So there are different variants of x86. So let us assume that we are talking about the 32-bit instruction set. And with that assumption, let us proceed. But clearly, if you know how to write assembly code for a 32-bit ISA, you can always write assembly code for a 64-bit ISA. All that you need to do is convert every register from EAX to RAX. Right? So you'll move from 32 to 64. That's pretty much all that you need to do. And there are some other instructions which will also change, but we'll discuss them when the time comes. Similarly, to move from let's say 16 to 664, AX will become RAX. So this is a very simple transformation that we need to apply. Similarly, going from 64 to let's say 32, what we need to do is that all registers of the form, let's say RAX or RBX, doesn't matter, will become EAX. So that's the reason it's not necessary to discuss every variant of the x86 instruction set separately. For example, 16, 32 and 64. So we sort of take the middle path and we discuss the 32-bit instruction set, and then the readers can do this simple transformation, which is just change the register name, throw out the E and put in the R, and it will become 64-bit compliant. As simple as that. It's not harder than that at all. So coming back to our present discussion, here we have a base register, where the base register can be any of the first 8 registers. Uh, Plus so this is a scaled indexed addressing mode that we can have, where again the scale is optional. So in this case, the index can be any of the first 8 registers other than ESP. So the ESP, the stack pointer, cannot be used as an index. So let me write that. Other than ESP or the stack pointer, right? All the other 7 registers can be used as an index, and optionally they can be scaled by a factor of 1 or 2 or 4 or 8. And then we can add a displacement. So a displacement is an offset, it's a constant. So we can add any displacement that we want. And in 32-bit instruction set, the displacement's maximum size is limited to 32 bits. So what does x86 do? It supports a base, a scaled index, and an offset. And the offset is known as the displacement. And mind you, each of these fields is optional. Alright, this is something which has to be kept in mind. Alright, so let me now give an example of addressing modes. So let us consider the memory operand as it is specified in the x86 assembly language. the value of the address in register transfer notation. So for this, go back to chapter 3. So it'll tell you what it is. So this is basically we are just mathematically trying to represent what the address is like, and then the addressing mode. So x86 supports many kinds of addressing modes. So one of the basic modes is a register indirect addressing mode, where the value of the memory address is stored in EAX. So we represent it as EAX with a square brackets on both sides. Then we can have a base and scaled index addressing mode, where it can be the address can be represented as EAX plus ECX multiplied by 2. So the value of the address is EAX plus 2 times ECX. So this is base scaled index. Similarly, we have a base scaled index offset mode, where the address can be of the type EAX plus ECX into 2 plus a displacement, which in this case is minus 32. Similarly, we can have base offset just EDX minus 12. We can just have scaled index, which is just EDX into 2. And we can just have a displacement, which becomes memory direct. So we can directly specify the memory address. So this is also allowed in this form. So let us just go back to the previous slide and look at this once again. Now that we have seen examples, see, you will be able to appreciate how and why this happens. So in this particular case, as you see, the base, the index, the scaled index rather, and the offset, all of these fields are optional. So the memory address can be any combination of these fields, as we see in this particular table over here, that we can have all kinds of combinations of memory addresses, and this makes the entire thing very interesting and slightly complicated. But if you understand the main idea, again I'm going back to this figure where we have a base register and another index register which can be scaled by a factor from 1 to 8, 1 to 4 or 8, plus a fixed offset or a displacement which is a constant. So basically, if this is the general format, we can start fitting any kind of an address in this format where one or more of the fields are optional and sort of not present. For example, in this case, only the displacement is present, but the base and the index are not present. Alright, so after taking a look at the machine model, which was by no means simple, we have done most of the hard and difficult and dirty work. So now we can appreciate the greatness of the x86 instruction set slightly better. So again, as I have been pointing out over and over, it's reading the book, listening to a video is great, but unless students actually sit down and practice and physically write assembly code, they will actually not learn or be effective programmers. So what I would suggest is that they can write assembly code. So an assembler and a runtime are there, not a runtime, but an assembler you can find on the book's website. So you can just go to the website of the book and type my name, go to the home page of the author and go to the website of the book. So you'll find a link to an assembler called NASM, NASM, and this can be used. There are many other assemblers, x86 assemblers as well, such as TASM or MASM. And so any assembler is fine, right? There is no problem. But we will be using the NASM assembler format, at least the format of the NASM assembler in this lecture. But other assemblers have similar formats, so the format per se is not that important. So the URL of the NASM assembler is www.nasm.us. And so this is a fairly easy assembler to use, and so you will find a lot of examples on the website of this assembler. And at least on the Linux system and on a Mac OS system, this assembler seems to work just fine. So the generic structure of an assembly statement is very similar to the generic structure of an assembly statement in both simple RISC as well as ARM. Any assembly statement can have an optional label followed with a colon, then the assembly instruction. And comments here start in NASM, comments start with a semicolon, not with an at, as has been the case earlier. So x86 assembly instructions typically have two formats. One is the AT&T format and the other is the Intel format, right? And the other is the Intel format. So in this book, we shall actually be using the Intel format. So the formats are more or less the same, but in the AT&T format, the destination comes at the end, which is not what we are used to. We are used to the destination operand coming at the beginning. So we'll use the Intel format. So there's something important to keep in mind because readers, listeners should know that both of these formats are out there, but you have to verify that the Intel format is being used. So typically most x86 instructions use a 1 and 2 address format, and so basically they can have one operand or two operands. So in the 2 address format, which is of this type, instruction operand 1 and operand 2, if we are using the Intel style, operand 1 is typically both the source as well as the destination. So essentially we will perform an operation on operand 1 and operand 2. Subsequently, we will save the result in operand 1. So operand 1 will get overwritten. So this is a standard format of x86 instructions. For the uninitiated, this can look as something new, but once you get used to it, I think it's fine. So in general, people get scared of the fact that the Intel x86 assembly is very complicated. That's not the case. So there is a lot of elegance in the instruction set, and it's actually very easy to learn. Once sort of the basics are in place. So what are the basics? Let me just repeat. So I'll just keep on repeating it several times during the slides such that readers don't forget. The first basic is the way that we define registers. So essentially AX, EAX and RAX are the same registers, but we are just using, is the same register, but we are using different parts of it, right, in a 64-bit system. That's point number one. Intel has a segmented memory model. So let me just write it. So in a 64-bit system, RAX, EAX, and AX are actually the same location in hardware. Is there different parts of it is being used. The next is a segmented memory model. This is something that we all need to get used to. What are the main components of the segmented memory model? Well, the main components are the segment registers, which give the start of the segment, and the GDT table. The segment registers previously used to give the start of the segment. Now they point to an entry in the GDT table, which gives us the start of the segment. To make this process faster, we have a segment descriptor cache, which is a small piece of hardware which stores some of the mappings that this particular processor would be interested in. So the table need not be accessed all the time. And we have the floating point stack, which is slightly difficult to understand, but hopefully we have understood it by now. Where the idea basically is that all the floating point values are saved in an 8-entry stack, and a register just gives the position of, so a register, let's say STI, refers to the ith entry of the stack. So once these three ideas are clear, we can proceed with the rest of the lecture very easily. So let us now look at some of the basic rules for operands for most x86 instructions. So both the operands can be registers. So which is fine. This rule was also there in our earlier instruction sets, ARM and uh, simple risk. So at most, so here are some additional points. So at most one of them can be an immediate. So both cannot be an immediate or a constant, right? That is meaningless. So one of them has to be a variable, which means stored in a register or memory. But at most one of them can be, but not two. At most one of them can be an immediate. At most one of them. Sorry, this should be M over here. At most one of them can be a memory location. So which means that you cannot have two memory locations as operands. And a memory operand is encapsulated in square brackets, which we have already seen. So what are the rules for immediates? The size of an immediate is equal to the size of the memory address. For example, in a 32-bit machine, the maximum size of an immediate is 32 bits. So what are some of the other rules? So we shall use the 32-bit flavor of x86 in this book, in this lecture. So the readers can seamlessly write, as I have said, 16-bit x86 programs, no difficulty at all. Simply use the registers AX, BX, CX, DX, SP, BP, SI and DI. So all the programs that we write can easily be converted into 16-bit programs. Sometimes some additional suffixes need to be changed in the instructions. But when that arises, essentially I'll tell you what needs to be done to write the 16-bit or the 64-bit variants of those instructions. But in general, converting a program between any of the three flavors, and the three flavors being 16-bit, 32-bit, and 64-bit, is easy. Only the register names have to be changed. So the readers can also write 64-bit programs by using the same set of registers, right? The R series, RAX, RBX, RCX, RDX, and the 8 new registers that are provided by the which are essentially provided by the 64-bit system, and these registers are actually should be, sorry, R8 to R15, right? Not R9 to R15, but R8 to R15. So next we will discuss what the individual instructions are like. And so this particular part of the lecture will end here, and the next part will begin with the move instruction and what it is like.